Thank you very much. Awesome. So I've muted everyone. So in case you want to speak, just raise your hand or put your questions in the chat. Please, we are going to have a very engaging and lengthy discussion on the notebook because I want you guys to understand exactly what Kolesh did to lead the leaderboard. It was not easy, I'm very sure, as he's going to say. And personally, I'm excited. I have my notebook here. I need to know all the small deeds that you need to do to improve your ranking on the leaderboard because, yeah, we need to oust him, right? We are coming for you, Kolesh. So Zindi, for those who are new, Zindi is a social enterprise whose mission is to mobilize a vibrant community of data scientists across Africa. We do this with outreaches, events, and yeah, we try to keep the community as vibrant and as happy and as cheerful and as engaged as possible. Now, for the girl behind the voice, I'm sorry I cannot put on my video right now, but I promise I'm not catfishing anyone. Oh, okay, let me see if I can start my video. Awesome, yes, I can. So my name is Ruth. I forgot to write my name. My name is Ruth Luta. I am the country ambassador to Ghana. I'm a West Africa entrepreneur in training, currently working on my startup. I was born and raised in Kenya. And a fun fact, I decided to take up DJing when I was here in Ghana because this is apparently the land of creatives and I'm loving it so far. Now, today's show is not about me, so let's move on to the main character, Mr. Stephen Kolesh, who was the winner of the UmojaHack 2023 Beginners Challenge. A little bit about Stephen. He's an introverted computer scientist. He was born and raised in Kenya. He's a Zindi University ambassador. He just completed his campus a week ago, excited. His hobbies when he's not working and doing nerdy stuff, he likes to binge watch. If anyone guesses whatever he's currently binge watching, I have a gift for you. And his hobbies include hanging out with friends also. So I'll give you a chance to guess what he likes, what he's currently binge watching on, and whoever gets it first, you get to win a prize. Thank you very much. So you can get typing. And now, in case you don't have the link to the notebook, this is the link to the notebook. And I'm going to pass it on to Stephen. Take it away. Stephen? Keegan, you are not right. Oh, Steve, if any of your friends reply, please let me know. I need to, maybe you're binge watching together. Okay. Steve.
Okay, hello guys. Can you hear me?
Yes, I can hear you.
Okay, my name is Stephen Kolesh. Oh yeah, I'll start sharing.
Okay.
You have to enable me to share.
Let me enable. Okay, enabled. Sharon, there's no cheating. Stop asking for clues. Awesome. Okay.
Okay, can you all see my notebook?
Yes, we can.
Okay, my name is Stephen Kolesh. I'm from Kenya. I completed my final year exams like 1 week ago, and I'm so excited for what the future holds. So today I'm going to take you through my winning solution. I'll take you through my thought process, what I did, and I hope it's going to be a fun experience and learning moment for you all. So my thought process when any is in the challenge is first to understand the problem statements, understand which type of problem it is, whether it's a classification or regression, understand the metrics which will be used, the evaluation metrics, then do EDA and extensive EDA. And after this session, you'll understand the beauty and the power of exploratory data analysis. And
Mm-hmm.
I'll spend most of my time here because it influenced my future engineering techniques. Okay, so before I start, I wanna give a big shout out to Niran. I guess I don't know his real name, but currently on Zindi, he's called Bola. He shared with me another notebook in a previous competition, which I learned a lot, and I inherited some of the things I learned from his notebook, this exploratory data analysis notebook. Also,
Okay.
I've seen David Gonzana. I also want to give a huge shout out to him because also he shared with me another notebook on which he won in a previous competition about air quality, and which I used some of his techniques in my engineering notebook. Cool. Now I'll start. So everybody knows we have to use libraries. Everybody knows pandas, numpy, matplotlib, seaborns. I'll not spend much time there. So yeah, we load the notebooks. I mean the files. Okay. In the description, we are told that the places come from different provinces in both train and test. So we have to confirm that. We need to know this because it's going to be important, very important in our cross-validation scheme. Uh, so we combine the lat and the longitude to find the location. Then we use a intersection to find if they're intersecting location in both the train and the test. So you can see that there were no similar location in both train and test. So you should keep that in mind while doing your cross validation.
Why?
Cool. The next question we are going to ask ourselves is, did all the sensors start repeating at the same time? Because we need to know this for us not to make any incorrect conclusions when finding the trend and other visualizations. So you group by the location, the year, find the mean. You can see they all started at currently there were some locations which started sending data from 2019, others started sending data from 2020. So not all places started recording the data at the same time. Cool. Any duplicate present, we need to drop duplicates because it helps us to ensure data quality, improve model performance, and optimize computation efficiency. So how we do this, we have to use a subset of location, year, and week number. Because if you use only location, you'll find duplicates. If you use year, you'll find duplicates. If you use only week number, you'll find duplicates. So you have to use both these three features to find if there's any duplicates. There are no duplicates. Shape of the data set, the number of rows and columns, everybody knows these. So I'll jump. Statistical summary, pandas.describe, df.describe, function to identify potential outliers, imbalanced distributions, or missing values in the data. So you can see when we do .describe, we find the means, the count, the mean, the standard deviation, minimum, 25%, and all that and all that. Okay, so how can we like uh, identify if they are missing values? We can see that in the training data set we had 74,005 rows, and when we come here at the counts, some have 72,000 rows, meaning that there are some missing values. How to find outliers? You can check that 75% and max, are they far off from each other? That's one way, but it's not the only way. And yeah, you can check in the standard deviation, the statistical summary of the data frame. Cool. Then we go to the missing values. We can drop the missing values or iterate to fill the missing values. But since this kind of owner of this data set might have missing values in the data set in the future, it is advisable to use machine learning algorithms and train on missing values, such as the GBDT models. They can handle missing values. But any data with more than 30% of values in the train should be dropped. But this is not it's not constant. You can choose your own threshold to drop the missing values. And as we'll see here, what's happening here, I'm creating a data frame with the percentage of missing values. Also, in this line, you can see I'm creating a list of columns to drop based on a threshold of 40%. As I said, this is not a constant. You can change it based on experimentation, which works well for you. Or you can also just fill it. But for me, what worked best, it was dropping them. You can see the percentage, and not many columns have huge percent of missing values, except these ones with 93%. So 93% actually, you have to drop them because they won't add meaningful data. They just bring randomness to your data frame. Cool. So here I'm dropping the columns to drop specified. Location value counts, just finding how many there were in the data frame. Obviously not equal distribution here because not all places started sending data at the same time. Cool. Now we go to geolocation. Geolocation is based on the latitude and longitude. Here I'm going to visualize the geographic distribution of data points in the training data set. So let me do this. We are going to view a scatter plot of the geographical distribution of data points in the training data set. Okay, this is not meaningful on its own. I'll show you which is meaningful. Cool, this one is meaningful. So the blue ones are the training data sets. I'm sorry, I didn't put here legend. The blue ones are the training and the red ones are the test data sets. So you can see there's no overlap as we saw earlier of train and test locations. But since these two here are nearly located, you can use k-means clustering to cluster them. This here, but this one is too far away. But you have to experiment. It's not a constant thing. You have to experiment. So what are you supposed to ask?
Yes? Give me a minute. I think I have a question from there. So are you saying, okay, no, just keep sharing. Are you saying that you have to check for both train and tests? Why? Do they affect in any way the validation?
Yeah, they affect the validation because if you use, for example, most of us use for regression problems, we use k-fold. K-fold cross-validation. If you use k-fold cross-validation with the training locations in the training data set, and the test has different locations which are not trained. You got? So like train has let me explain like this. Train has different location. Let's say if you're talking about countries, train has Kenya, Uganda, Tanzania, Nigeria. Test has Somalia, Djibouti, Africa, Zimbabwe. See, the distribution in train is of different countries. And now you're trying to use the data of those countries to predict data of another country, which is not the right thing to do.
Oh, okay. Now I get you. Now I get you. So let me ask you, would merging the train and tests? No, but then
imagine the train and test won't help because you'll later have to separate
them.
Yeah, and they will still have both unique train and test distributions.
Okay, now I get you. Give me a minute. Are there any questions, guys? I know he's moving a bit fast. Are there any questions that maybe you have not understood? Kolesh, if you could relate what the EDA that you're doing with the purpose, like the objective at the end, I feel like that would also be of help to help us understand exactly how your EDA is moving towards the objective of the whole hackathon.
True. Yeah, I'll get to that.
You'll get there. Okay, cool.
Yeah.
Let's go.
Okay. So how are the sensor locations near or far to each other? It is clear test and train all come from different distributions. So questions you can ask yourself: different provinces, different readings, same country, same readings. Some test location areas, some train locations. So we can cluster them for FA using k-means, as I had explained earlier. Cross-validation should also follow the distribution. So for example, how is this EDA of geolocation related to the objective function? First, you can see it helps us understand that the cross-validation should put into consideration that these two have a different distribution and should employ the same in our cross-validation scheme. And also, it gives us an idea of how we can use k-means to cluster them by looking at which locations are near each other. For example, this and this. So from this, we can get how we to cross-validate and what kind of feature engineering techniques we can use. Cool. Assess on feature distribution to the emission distribution. Like you just want to see how they relate, the relationship. And in this one, I didn't find any meaningful relationship, so I'll move on to the next. We'll look at distribution for one feature. We can see that this follows a normal distribution. The distribution is it that bad really? No. What to look for? To look for skewness and outliers. Why? Because while knowing if the data is skewed or not, we can choose the right model or pre-process accordingly. I'll show you that later. So we are going to look at the target, which was emission distribution, and I'll plot some plots: a box plot, distribution plot, quantile plot. Okay, so in this, what can you get from this for example, the data is highly right skewed. The target is highly right skewed. Also, we can see this gap. So why was there a gap? So we can see this gap in the quantile plot too. Now, why are these distributions important? You have to question them. Why the gap? Data skewed? Yes, right skewed. How are we going to deal with it? So there are a lot of transformation we can do on the data set when it's skewed. We can square root transform, we can cubic transform, or we can box Cox transform. But these are not constants. As I see, data science iterative process. You have to experiment. Not everything works for the same problem. So you have to experiment what works for you and what work for you. So we in this, we are going to experiment with one, and we will see how these distributions change when we pre-process the targets. So we are going to power transform the targets, but you can, as I said, you can use others, and you'll see the huge improvement in the distribution when we power transform. Cool. So earlier, you can see how the target was highly rapid. But after power transforming, you can see it's nearly following a normal distribution. We cannot see the gap anymore. So it looks really good after power transforming. Now, the question you have to ask yourself, should we power transform it in modeling, then transform it back? And does it improve your model? Experiment. So experiment. Whatever you find here, experiment. Does it have any influence in your model? If it doesn't, then there's no need of putting it, but at least you visualize and so that this can lead to a good improvement. And most cases, they lead to huge improvement in the modeling phase, but you have to experiment. It's not a constant. Cool. Now we're visualizing all numerical data. We want to see how the distributions skewed data, which follow a normal distribution. So this is going to take a lot of time because there are a lot of column, so I'm going to comment this, but you can try it on your own. Okay, I had tried it earlier, so you can see how you view the distributions of each column in the training data set. So right skewed, right skewed too, but not highly. Yeah, you can visualize maybe this follows a normal distribution. Then you can transform it accordingly based on your experiments. Cool. Now the most fun part is of this EDA is understanding the trend. This was a time series like problem, but we are going to see if it really was a time series problem. Understanding the trend. We are being given the week and year. Since the goal is to predict weekly emissions, we can also add the month. Since we are not given the month, we had to create the month for ourselves. So we can also add the month to study weekly, monthly, and yearly trends. This is also where most of the feature engineering ideas come from: lags, rolling means, seasons, etc. If there are clear monthly or yearly patterns in the data, we may want to use rolling means or lags that correspond to these patterns. So why are we doing this EDA? Now questions back to the objective goal. If there are clear monthly or yearly patterns in the data, we may want to use rolling means or lags that correspond to these patterns. Cool. Now get the month. Okay, that's self-explanatory. We are getting the month from the week and year. Change month distribution. How the months distributed yearly. So I'll show you why we needed to do this. This will explain it better. In one plot. You can see the train month distribution and the test month distribution follow the same distribution. Like this high is the same high with this high is the same high with this. And what can we learn from this? If you have the same years in both train and test, then is this series problem? It's not a time series problem if you have the same years and months in both train and test. Then this gets back to being a normal tabular regression problem. So where we need to use a time series cross validation, no, we don't need to use a time series cross validation because we have both train and tests with the same month and yearly distribution. Cool. Also, train and test have similar monthly and yearly distribution, meaning the data has been split using this feature. Also add a different location, meaning we should have a CV scheme, validation scheme that resembles train and test not having the same locations, and train and test having similar monthly and yearly distributions. And we are going to do this in the modeling notebook. Cool. Yearly trend. Now we experiment using to visualize the yearly trend to see if there's a trend in the data set. Let it load. So we can see. Let me reduce this. Cool. So 2019 trend, 2019 follows 2020 trends, follows 2021 trends, follows 2022 trends. We can see that clearly these are yearly trend. To do more experiments. These are monthly trends. Month one. Okay, let me do this. Cool. So we can see month 1, 2, 3. they are kind of on the same trend. Then month 4, 5, 6 form the high of the trend. Then month 9, 10, 11, 12 trend again. So month 1, 2, 3, and 9, 10, 11, 12. But I'll plot one which shows this clearly. Cool. This, you can see that the start of the year starts slow, then builds up, then goes slow again. So with this, month 1, 2, 3, 4, nearly the same pattern. 5, 6, 7, 8, nearly the same pattern. 9, 10, 11, 12, the same pattern as this. So from this, we can create uh, season-like pictures. Like you can bin month 1, 2, 3, 4 in one bin, 5, 6, 7, 8 in another bin, 9, 10, 11, 12 in another bin, and create those new features. Clearly, this data is trendy, right? I believe there's a cyclical trend in this data. Observe January and December. January and December. They seem to have the lowest emission reading, while April, May, June, July are the highest. Can we create a feature that clearly explains this? So from this distribution, yearly distribution, monthly distribution, we can ascertain there's a trend, a cyclical trend. So this influences your feature engineering. We are going to see that in the modeling phase. So what you can do, PD cuts or bin yourself manually. I'll show you an example here. So Jan to April, create bins for Jan to April, May to September to December. Then, yeah, you create those bins. Now we're going to see another visualization of the trend. There is a beautiful trend in the data. Notice the yearly trend, amazing. Cool. Let us investigate for one place at a time. We're going to investigate. Now, this was for all locations in the training data set, but now we can minimize this to one location to see if each location follows the overall distribution. Cool. So we're going to find one location from the head. Now we're going to replace and create the distribution for that one location. Cool. Actually, this explains it way better. So we can see the beginning months, then high formed, then going back to the low in the December months. So, and we can do this we can experiment the other location. So I used the first, and you can use it with the other locations. You can do that for yourself. Cool. Location one follows the aforementioned trend. Amazing. You can study this trend and use it for rolling means. Let's get back to the geolocation. Remember when we were looking at the geolocation distribution, we said we can cluster them and form new features. But is that make it an assurity that you need to cluster? You need to experiment. Is it adding any importance to your model? Is it improving the score? Is it not? Then you have a useful feature by visualizing. So let's get back. We are going to use inertia and silhouette here, then experiment with the elbow method too. But here we are going to use the inertia and silhouette. And so we print our inertia and silhouette. So how can we use inertia and silhouette? A good clustering algorithm should result in low inertia and high silhouette scores. So when we come back to inertia, we have to find one with the lowest inertia. Lowest inertia is 111. So that's cluster 15. And 15 clusters came in with 15 clusters. And what is it? Its silhouette. Silhouette is 0.779. Also the highest. So 14 clusters has the 14 clusters has the lowest inertia of 111 and highest silhouette score of 0.779. We'll add these clusters later. But after I added these clusters, I thought it was not helpful as I was getting different clusters in the train and the test. So I never used it. So what can we conclude from the EDA? EDA is one of the most powerful tools of a data scientist. Why? through EDA, we have learned about the cross-validation scheme we need to use. We have learned about the yearly trends, which is useful. We learned about k-means. We saw that some locations could be clustered, but after experimenting, we saw that I saw that it was not helpful. But this is just conclusion. Some important insights can help the model. Others want it to experiment. And I want to emphasize this enough. Data science is an iterative process. Nothing is guaranteed. Experiment, experiment, experiment. A
Okay.
lot of experiments. Cool.
Okay.
Now you
Steve,
can ask me questions about the EDA notebook.
thank you, thank you, thank you. I thought you move on to predicting. Wow. So let me ask you first of all, when do you decide to do the EDA? Like, did you run the starter notebook from start to finish first and then see how the accuracy was before the EDA? Or this is something that you do normally, even without checking the models first before you start tuning?
Yeah, so my pipeline is EDA first over everything. Like I have to understand the data before I do even create the baseline. I have to understand how this data flows, how this data looks like, so that when I create the baseline, I have already and prior understanding of the data before I even do anything else. Everything will be influenced by how I have understood the data.
So what if you add features? What if like the features that you're creating don't really do much to the model? Do you still do it fast or
okay, so see here, I first started with the EDA, right?
Yeah.
So next I went to create a baseline. So first I added these k-means, I added the bins, I added the restraints, then all these features are learned through the EDA. So I was like adding and looking at the school, is it improving or not? If it's not improving, stop it, because why do you need a feature which you saw clearly in the EDA? Yeah, it's a good feature, but it's not helping the model. It's of no use. So you
Okay.
just yeah.
Okay. 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 So questions, guys, feel free to unmute and ask your questions before we move on to the predicting algorithm. I know this was quite thorough. I actually didn't know that you do this thorough in the one. I feel like, okay, what was I doing?
Especially for this time like tabular data set, you have to do a lot of EDA because you have to understand the trend. Trend is the most important thing. Like in time series, trend is the most important thing. So yeah, you have to do this. You have to do this. A lot of people can argue that UmojaHack is only 1D, so you don't need to do EDA. You just need to create models, stack them, stack them, stack them. But for me, I just love EDA. I just go into the data first before creating any model.
Okay, I really appreciate that. EDA is gone there. So, okay.
Yeah,
All right.
it's amazing.
I like how you are having fun. You're like, so the best part, and I could feel your tone going high. It's like, wow, I was having a time of my life doing EDA. Israel has a question.
Yeah.
Israel, let's go. Oh, sorry, I keep muting you. Sorry, unmute.
Okay, hi Steven. Thanks so much for the section. So I wanted to quickly ask about the location, like you mentioned in the test and the train. So I want to ask that. I know possibly you're going to still talk about that in your modeling, how you are able to handle that to ensure that the model performs better. Or what should we do, even before moving to model after identifying that the location, which is supposed to be a very important feature, I guess. So how are you supposed and do that validation when you are sure that it has different values across the train and the test? Thank you.
Cool. So how to make sure that your train and test have different locations? So one way you can do it like manually. You can select random data points for different location in the train. You can do a train test split where train has different locations and also the test has different which mimics the holdout test set which you have to predict for. But I did that. I experimented with that. It did not help my model. So the other thing you can do to make sure that the model does not rely on the location, you drop the location feature. You drop the location feature, but before you do that, you have, which I'm going to show you that in the modeling phase, but you can drop the location so that the model will not rely on the location features to predict prediction. Yeah, I'm going to show you in the modeling phase what I did.
Awesome. So guys, can we move on to the next notebook? So because I see you had 2 different notebooks, did you have to save the data set and then now go load it again, or what happened?
Yeah, you start from scratch. Now you don't have this EDA anymore. It's purely feature engineering.
Oh, okay.
Yeah.
Interesting. Well, all right, let's I wish you were,
Good,
if I was close to you, I would have brought you some soda or water. I know it, that was, but
yeah, it's good.
guys,
Okay,
you can
so
feel free to refresh and then we start this right now, I think. Okay, let's go
yeah. So this is my modeling notebook.
Mm-hmm.
So same pipeline. Load the libraries, load the data, reducing the memory function. This is just to preserve memory. And then removing nonce with missing values. Like as we saw earlier in the EDA, we have to set our own threshold. And as we looked at the percentage of missing values, we only saw that a few subset of the columns had 93% of missing values. All the other less than 5% of missing values. So that's why I chose. I'm going to show you. This is the threshold I used, 0.8, because all the others had less than 5%. Only a few subset had 0.93%. This could even go up to 0.9. It doesn't matter. So you have the nonce, view the shape, feature engineering, and cool. So what I did, create the location feature, then a created month feature, use it, which is useful in micros validation, which was useful in micros validation. As you saw in the EDA, train and test had similar yearly, monthly distributions. Dropped all angle, altitude, depth, and height columns because they had a low correlation to the targets, as seen in the starter notebook. So this was in the starter notebook, and I never showed this in my visualization. Angle, altitude, depth, height columns. I only relied on the density columns. Cool. Also extracted trigonometric features and periodic spline-based features to capture the cycles, inspired by David Nkosana's winning notebook in air quality. Shout out David Nkosana. I've seen you on the meeting. So yeah, it really helped me. Created rolling means of 26, 52 weeks to capture the trends in the EDA notebook. Created location-based. Cool. So let me just go to the code. First, I concat the chain and test. Then this was just to create the location feature, minimize the floating points. Okay, sort by location, year, week, number, angle calls, select all the angle calls in a list. As I had said earlier, I was supposed to drop these angle calls because I never relied on them. Shift calls. So these ones were used to create my rolling means. So you create a list of your columns which will create your shifts and rolling means. Create the scene transformer, cost transformer for the cyclic feature engineering, then periodic spline transformer. All this was inspired by David Nkosana. Cool. Get month. We saw why we needed that. Cool. So what does trigonometric features do? So the idea behind using trigonometric function is that they can represent cyclical patterns in a more compact and interpretable way. In particular, The sin and cos functions can be used to represent cyclic patterns that have a time period of 12. We saw that January and December resembled each other. And also when we do the yearly trends, we saw that each year follows the same trend. So like to get the cyclical trend, we had to get the cyclical features to represent that trend. So I want to go in math part. The sing function creates a wave and blah, blah, blah. You can read that for yourself. So yeah, created month sin and month cos. Cool. Periodic spline-based features. So what does this do? Splines are a type of piecewise polynomial function that can be used to capture nonlinear patterns in the data. In this case, periodic splines are used to capture cyclical patterns with a period of 12, such as the months of the year. So created the splines for the cyclical features. Nice. For call and shift call. Okay, this I could have called it rolling calls because I never used shift. I don't think I used shift. Yeah, I only used rolling statistics. So rolling statistics. What are rolling statistics? Statistics refer to statistical calculations that are performed on a rolling window of data points. The window size is specified by the window parameter. This window parameter in our case, since we are using weekly emissions, like it's the number of weeks you want to use as your window, number of weeks you want to use as your window. So this creates rolling statistics features for each columns in shift calls using different window sizes. Specifically, it creates rolling mean, rolling max, rolling minimum, rolling sum, rolling standard deviation, and rolling skewness features for the window size of 39 weeks. The window is equals to 39, window is equals to 52. So this represented yearly statistics. 17, this represented quarterly statistics. 17 weeks, 52 weeks, 39 weeks. This represented 3/4 of the year statistics. Why? This was inspired by the trend, right? Like January to March has its own trend. Then January to April, then April to I guess September, then September to December. So like I created 3/4. I mean the yearly first, the yearly trend, then quarterly statistics, which is represented by 17 weeks, and then 3/4 statistics represented by 39 weeks. Then created mean, max, minimum, sum, all those statistics. Cool. So question by Idiaju, Israel. So how did I ensure that my model did not rely on the location? I first created location statistics. So how this works is by dropping the location column, the model cannot simply memorize the relationship between the target variable and that specific location. Instead, the model has to learn the relationship between the target variable and the other features. These new features here that capture location-based statistics. This can help the model generalize beta to new locations that are not seen during training. So I'll give an example. Remember when we were supposed to k-means cluster the two locations which were near each other? Those two locations, since they are located near to each other, but they come from different train and test distributions, we can find this statistics. So those two locations can have similar statistics, So by capturing statistics and dropping that location, so it won't rely on the training location. No, it will rely on those statistics which have been created. And remember, they're near each other. They may share some of these statistics, but that is up to the model to decide. You have to experiment. So you drop the location, but before you do that, you create location statistics in such a way that locations near each other may share the same statistics. Cool. And if they share the same statistics, means that those same statistics, the test will have those test statistics. Instead of training with a location where train has its own location, test has its own location. Cool.
Okay, wait a minute. Steve, let me ask a question. In what other types of data sets can such logic be used? Because I really like the
In
approach.
what?
In what others kind of because you said that you got this from Concerna's notebook that he did in Airco, right? So
Oh,
is that
yeah. These cyclical feature engineering
yes,
stuff.
yeah.
Yeah.
In what other types of
So okay. So what other types of problems can this be used in?
exactly?
Oh, cool. Uh, in most parts, I've seen these features, the cyclical features, be used in. Oh, okay. In regards to Zindi, I saw. Okay, the Guasana used it in layer air quality, because that's sensor data. Any time series related data can use this. Also, what's it called? There was this fossil demand, I guess. Fossil demand was a time series for sales. I guess that can be used also in that scenario. What other? I guess any time related data sets can be used. This can be used. Sensor data, sales and demand, and all that other time series. Sleep patterns. Yeah.
Okay, thank you. Let's go.
Cool. So actually the featuring stuff has ended. So you pre-process, you have a huge amount of data sets. What you can do here, you can drop some of these columns by finding the correlation, but I never had time to do this. But these features are really helpful. So we'll go to the modeling. So you can see I dropped the location here after creating the statistic. So you create your X and Y. Now, where did I use the same yearly and monthly distributions? It's a month column because in my EDA, I found that the other than different location, the test and train was splitted according to the month. So I used, instead of a normal K fold, I used a stratified K fold based on the month because as I saw, both train and test had been splitted in this feature. And actually this cross validation scheme can improve your score. You have to experiment too. Maybe my pipeline was different, but it really helped me. So yeah, I used it here, created a stratified key full of 12 of splits, uh, trained a LGBM regressor with these params, and yeah, created my validation score. So I don't. It will take a lot of time to train, I guess. So yeah, we are going to talk about these other sections as it trains. Cool. So let's visualize the feature importance. You can see my main features or the statistics which are used. Location mean based on the density index, location mean. Yeah, so that feature engineering alone uh, really improved my score. And also, I know a lot of you guys struggled when you are using Kfold. You only saw a portion of features being used. For example, you'll see like 5 having these huge bars, then all these others have like zero importance. I guess it was overfitting somehow, but glad I did manage to create a good pipeline for my model that never did that. So as you can see, the location statistics really helped my model. It really did. Cool. So another trick I used to boost my score. Actually, this was the game changer. If anyone was keen, me and this guy called Heyu, we were really struggling with each other. Uh, jumping schools, jumping schools, jumping schools, jumping schools. This is because of blending. So first I trained LGBM using Kfold, I mean stratified Kfold, then used a cut boost later, trained on the whole data set. Then after training it on the whole data set, see, this was taking a lot of time, 1 hour, 42 minutes. So I won't run it. And then I took an average sample. Okay, in my final pipeline, I did not use an average ensemble, but these alone will put you in number 2. Is my secret cookbook. So yeah, but this alone is good enough. So after this ensemble, this gave me a very huge boost. Yeah, not that
Wow.
necessarily the ensemble technique I used, but this does the trick too. So yeah.
So you spared your winning notebook, eh? Wow, I like that. I do you know what, that most of us just did the LGBM and left it at that, but you decided to come and blend. Wow, okay. So Israel, what did you do for those of us who took part in the beginner challenge? Like what
Yeah, the blending really helped.
Yeah, if you did not blend, have you noticed that it helped? And are there some of the things that, oh wait, Stephen, are you done?
Yeah.
Okay. Okay, I think now we can take some questions and have a brief discussion. So please feel free to unmute and let's talk. So Israel asked, what do you suggest to improve any of the models? Both, I think you can keep sharing, Steve. Both, what is it called? The LGBM and the cat boost before you now ensemble them together.
What really helped me? Yeah, so as you have seen in the feature, all these location statistics really boosted my model. So actually, it's really improved because you can see the top 50 alone are the location statistics. So yeah.
Okay.
This feature engineering technique here. Yeah.
All right.
Hello, everyone.
Hello.
Hi. Okay, my name is Emmanuel from Kenya. So I have 3 questions. Number 1 question is, how much time did you spend on EDA and maybe on training, considering the second question is, in your EDA and collab for training, is there any particular reason for that? And the last question is about the models. The models out there. Did you particularly try on LGB and CatBoost directly, or try different models before settling on these two? Thank you.
Cool. Okay, I've not gotten some of your question, but I guess the first one was how much time did I spend on EDA and how much time I spent on training, right?
Yeah.
And the second question was about.
The question is about, in your original notebooks you shared in your GitHub. You use Kaggle for EDA and Colab for training. Is there any particular reason for that?
Okay, and that question?
It's about the model.
Oh, cool. So first question, how much time I spent on EDA, how much time I spent on training. Cool. So UmojaHack started at 12 EAT. So first, I started with the intermediate competition. Then after some time, I got back to the beginner challenge. Then I spent almost all that afternoon in my EDA. It took me about 2 hours 30 minutes on my EDA. Then all the other time was spent on trying the features and training and evaluating my model. Also, I did hyperparameter tuning the night before the deadline. So yeah, that also helped me. I did hyperparameter tuning. It was taking a lot of time. So when I went to sleep, I left my notebook running. So yeah. So EDA, I only spent EDA 2 hours 30 minutes on EDA. Then all the other time was spent on training, hyperparameter tuning, model evaluation, etc. Cool. The second, why the notebooks I sent, one was the EDA was on Kaggle. The notebook itself was on Colab. The reason why the notebook was on Colab is because when Zendi asks for the winning solution, it needs to run on Google Colab, and they only want modeling notebook. They don't want the EDA notebook. So I had done all my experiments on Kaggle because they offer you 30 hours GPU and a lot of time. I guess they don't have a limit on the CPU. So yeah, I spent most of my time. I mean, all my experiments, both the EDA and the training, were done on Kaggle. Then I later transferred it to Colab before submitting my results. So like, there's no main reason why I used Colab on training and Kaggle on EDA. You can use either. It's based on your preference. That question. I'm in love with CatBoost. CatBoost is my go-to model, but it's too slow and it takes a lot of time to. So the next model I use is LightGBM. I use LightGBM and I use CatBoost in all my Kaggle. I mean all my Zindi competitions. Why? I don't know why I hate XGBoost. I don't know why. It's because of you need to be really good at tuning an XGBoost to perform better. But currently for me, and because LightGBM and CatBoost has won me a lot of competitions, I'm in love with those two. So it's based on your preference and experience, I guess, on which models you use. Yeah, I hope I've answered all the questions.
But it definitely comes with so much practice. I think you
Yeah.
rank highly on Zindi because of the number of competitions you've actually participated in. So yeah, kudos.
Yeah.
When you get to say which algorithm you prefer and don't prefer. I like that. And you already knew that you
Yeah.
had a winning notebook somewhere, bro. It's okay. Let's not be careful
Yeah.
about it. All right. Are there any other further questions?
Also, please, just something to add on. David Kosana, like, I wish everyone saw his notebook on layer. I mean, amazing. He used PyTorch Lightning temporal fusion transformer, which is a technique on how to deal with, time series like data. But at least for the layer, it was time series, full time series, not like this where you have the same monthly and yearly distributions. But if it is a full time series problem, you should check out about. I don't know its real full name, but it's something to do with temporal fusion transformer. Yeah, it's a really good deep learning model. Yeah.
I think, Konsana, I will take up the challenge and do the airco, then bring you on for discussion. Or if you want to host a discussion, please let me know. But I'll be in your DMs very soon. Don't worry. Thank you so much, Stephen, for appreciating your references. Also, I feel like that's really part of it. We go to GitHub and steal some code snippets here and there, and you do not get to appreciate wherever you got them from. So
yeah.
Thank you. You really reference them a lot. Like, I was like, okay. I'm happy that they get to see their work being
I've been pushing that on Zindi.
That's true, by the way.
Yeah, winners should be posting their solution and like explain to others what they did, yeah. So everybody can learn. Yeah.
No, because for the winning notebooks, I get that a lot, even from like the advanced one. People just post the code and it's one function. What am I supposed to understand from the one function? You have scripted the whole code and then you gave us, now take this. This is the winning one. I'm like, okay, now what do we do with this? But thank you so much. Wow.
Yeah.
If there are no further questions, I think, I know, Steve, you have spoken a lot. Thank you. Like, you did not even hold back. Let me stop the recording so that we don't record spam.